Have you ever wondered how to ensure the reliability of your linear regression model? Are you curious about the assumptions that underpin this model and how to validate them? Well, you're in the right place. Today, we're diving deep into the world of linear regression model assumptions and the tests that can be used to verify them. First off, let's unravel the mystery of the linear regression model. It's a predictive statistical method that attempts to model the relationship between two variables by fitting a linear equation to the observed data. But here's the catch. The success of this model hinges on the validity of several assumptions. If these assumptions are violated, the model may lead to misleading or inaccurate predictions. So, what exactly are these assumptions? There are four primary ones: linearity, independence, homoscedasticity, and normality, commonly abbreviated as LIHN. Before we dive into the LIHN assumptions, let's discuss a pivotal prerequisite: multicollinearity. This assumption dictates that the independent variables in our regression model should not be highly correlated with each other. Why? High correlation amongst independent variables can inflate the variance of the regression coefficient estimates, leading to unreliable and unstable estimates of the model parameters. We can detect multicollinearity using a statistic known as the variance inflation factor, or VIF. If the VIF of a variable is high, say above 5, it means that variable is highly correlated with other independent variables and it may be problematic. However, if the VIF is less than 5, it indicates the absence of multicollinearity, so it's crucial to check and validate this assumption before moving to the LIHN assumptions. Linearity presumes a linear relationship between the independent and dependent variable. Crucially, it's important to check the linearity visually through plots. Additionally, one can employ a quantitative measure, the Pearson correlation coefficient, to confirm linearity. The value of this coefficient will dictate whether your relationship is linear or not. Remember, if the correlation coefficient ranges from -1 to +1, you're on the right path. Scene 6. Independence assumption begins now. The spotlight is on independence, in which it is assumed that residuals are operating independently from each other. Checking for this independence is where Durbin-Watson Test comes in play. A glance at the test statistic reveals that a figure thereabout 2 suggests an absence of autocorrelation. Wrapping up, it's notable that the test vacillates from 0 to 4, with a value around 2 signaling no autocorrelation. Opening with homoscedasticity, an intriguing term that might seem straight from a science fiction film. This concept, however, isn't as alien as it sounds. It simply signifies that the dispersion of the residuals stays unvarying across all the independent variables' echelons. Moving on, we delve into the heart of homoscedasticity and its undeniable significance in statistical scrutiny. We then the two principal methods for confirming homoscedasticity: the Breusch-Pagan test and the White test. Finally, we decipher the cryptic p-value to ascertain homoscedasticity. As we conclude, remember this golden rule. If the p-value surpasses 0.05, the data is homoscedastic. Our last topic focuses on normality, an assumption that implies residuals follow a normal distribution. The concept of normality is closely related to residuals. To determine if the data adheres to this assumption, there are two prominent methods. One can opt for a visual check using a QQ plot or a quantitative check via the Shapiro-Wilk test. The result of the Shapiro-Wilk test is interpreted with the help of a p-value. If this p-value exceeds 0.05, it indicates that the data is normally distributed. To wrap things up, it's vital to engrave in your memory the 5 assumptions of a linear regression model: multicollinearity, linearity, independence, homoscedasticity, and normality. We have distinctive tests for each of these assumptions: variance inflation factor, VIF, for multicollinearity, scatter plots or the Pearson correlation coefficient for linearity, the Durbin-Watson test for independence, the Breusch-Pagan test or the White test for homoscedasticity, and the QQ plot or the test for normality. Validating these assumptions is imperative for precise regression analysis. This is our summarized overview of the linear regression model assumptions. Ensuring the reliability and accuracy of your linear regression model is as simple as taking the time to verify key assumptions. This pivotal step can lead to more informed decisions, heightening your decision-making process. The next time you work with a linear regression model, it's crucial to remember, checking your assumptions isn't just commendable, it's absolutely necessary.